Devesh, you can start.
Yes. Good morning, everyone. I'm Devesh Bajaj, and today I'll be your host. I hope you are strong and healthy. We'll be resuming our math club activities with the foundational course series. This is going to be the first lecture in the series. I have with me Master Sanchayan Bhowal, who will be introducing us to rings and modules. So, without wasting any more time, I hand over to Sanchayan.
Hello, am I audible?
Yes, you are audible.
Yeah, yeah. Okay,
Yes.
let me share my screen. Okay, hopefully it's shared now. Is it visible? Hello.
Yes, it is
Yeah,
Yeah.
yeah,
visible.
Okay. So, this is gonna be the first lectures of the lecture series of rings and modules. So, this is gonna be a brief lecture about the motivation for rings and the definitions and some examples and some properties of rings. Okay, so let's start. So we uh, started our abstract algebra with groups, and groups had these following properties like closure, associativity, existence of identity, existence of inverse. And we have seen many properties of groups, abelian groups, and many things. And these are some popular examples that we have already seen. Now notice that this does not have only one binary operation that we had in groups, just a one binary operation like multiplication, addition, or composition, anything. But there was only one. However, in arithmetic, we find many different operations like plus, minus, multiplication, divide, and minus can be considered as a addition of inverses, and again, division when considered as a multiplication of inverses. So we'll start with, let's say, the group R and under addition as a binary operation. So we take Z, for example, and I take two elements, A and B. Now we can obviously add them to get A plus B, and that will be in Z. Moreover, we can multiply. We can multiply and we will get an element which is already in Z. And this is not only the property of Z. Similarly, we can see this same property in Q, R, C, complex polynomials, matrices. You can multiply matrices. Obviously, they need to be of the same orientation. Otherwise, we cannot multiply to get another matrix. Similarly, for polynomials and for this ZQRC. So we try to encode this information of multiplication somehow to this group. So we define this new structure, we put this multiplication here, and we define this new structure to be rings. Now this is not a definition, we are just like trying out things. So now we will find the definition. Now what is the definition? For addition, we have just the definition for groups. Moreover, we have commutativity here, which was not there in the groups. That is, the rings need to be an abelian group under addition. And in multiplication, we have closure, associativity, commutativity, and existence of identity. Now note that you need to take these last three with a grain of salt because there are some exceptions like non-associative rings, non-commutative rings, and rings without identity. And mathematicians are very bad at giving names, so they just omitted the I here. And this is also known as rings only. And we are not bothered about these three. We will discuss, and our whole lecture will be discussing about commutative rings. Okay. So yeah, another most important properties that I missed here, that is the distributive property, because we don't just have plus and multiplication, we need to associate them. So how do we associate them? We introduce the distributive property that we have already seen in our previous classes in high school. Okay, now let's take some examples. Now here I will give a non-trivial example, not like ZQRC. So I take a continuous function, let's say this thing, odd looking, and I call it fx. And I have another one, I call it gx. What I do, I add these values. Like for point 0.4, I have this value here and this value here, and I add them. Similarly for point 0.2 and for all 0 and in between 0 and we get this curve, let's say. And this is again a continuous function. As you know, adding to continuous function is again a continuous function. Similarly, we can multiply and we'll get fx and gx, fx times gx. And as you know that these two are continuous again. So we can say that continuous rings forms a ring. Sorry, continuous functions forms a ring. So we take the interval as 0 and 1 and we define all c 0 and 1 to be all the continuous function from 0 and 1 to r. Now what is so special about 0? There is nothing special. So we define it in all real life. Now again, what is so special about continuous function? We don't need continuous. We can define it for any metric space from x to r and all the functions from x to r. Okay. Now we define real polynomials. Again, real polynomials is a special case of continuous functions, so it will always form a ring. That is, if we multiply two polynomials, we will again get a polynomial. Now let's take the example of real polynomials. So we have it like this. We have all the polynomials and these coefficients are from real because we are taking real polynomials. And we define addition. How do we define? We compute the value of px, let's say, at x and compute the value of qx at x, and I just add them. And similarly, I multiplied them, and this has this following expression. And I get what is known as the real polynomial ring, and it is denoted with this fancy notation. Now, again, what is so special about real? We can do it for z, we can do it for q, we can do it for c. So we further generalize it and we put R, that is any ring, in place of real. Now, why do we require ring? Because otherwise, this addition and multiplication will not be defined. Neither distributive property will hold. So we require this ring structure here, and the coefficients will come from the ring, and the variables are as usual. Now we further generalize it and introduce formal power series. What is this? Now this is a never-ending polynomial, let's say. So it continues, continues, and continues. Like, don't we are not bothered about all if this series converges or diverges or anything. And consider these as a sequence, a1, a0, a1, dot dot dot. Now how do we add them? We add component wise, and similarly we multiply them. Now this the motivation of this came from the polynomial ring, where we had n. Here we had n. Now we just replace this n with infinity, and we multiply. And this is the notation for it, and this is known as formal power series. Okay. Now here comes some important properties or important definitions before going into theorems. So what are zero divisors? Zero divisors are those elements which when multiplied with a non-zero element in the ring again, we get zero. Now for example, let's say z mod 6z. Z mod 6z. Now this forms a ring under plus and multiplication. Yeah. Now let's take 2 bar in z mod 6z. Now if I multiply with the 3 bar, which is non-zero, I get 6 bar, which is same as 0 or 0 bar, whatever. So 2 bar is a zero divisor. And a ring with no zero divisor is integral domain. Okay. This is also sometimes called domain, just domain. Okay. Now some more definitions. Units. Now what are units? Units are those elements in a ring which have a multiplicative inverse. Sorry. Now we take the set of all units of R. Sorry for that. Yeah. Take all the units of R, and now notice that this forms a group under multiplication. Now why is that? Because everything has a multiplicative inverse and other properties already hold. Now we'll take some examples. Let's take F star. Now what is F star? So F is a field and F star is the set of all units of F. Now in F, all the elements are multiplicative inverse except the 0. So what will be this? This will be just F minus 0, singleton 0. Okay. Now let's take another example, that is even F star. Now, what are the matrices that have multiplicative inverses? And these are the non-singular matrices of elements taken from F. Now, this is nothing but just the GLN group or generalized linear group, and which take the elements, take the entries from F. Okay. And this, as you can see, this also forms a group, this also forms a group. Now I will leave this as an exercise. You can try this out. What are the units of this ring? That is the formal power series. Okay. Now we had something to relate groups, two groups. A function which preserves this binary operation structure. Now we'll try to do it similarly for the rings. So we have two rings. Again, we define a function or a map which satisfies these properties. As you can see, this is needed here because for the groups we didn't need this because this thing came as a consequence of the binary operation, because um, there we had identity, multiplicative identity, or sorry, multiplicative inverses. But here it is not possible because in a general ring we don't need multiple inverses for all the elements. So this is required as a condition. Now let's take an example. So this is known as the evaluation homomorphism. So what I do, I take an element from real line and I take a real polynomial and I just evaluate it at a, and I get f of a. And this is a homomorphism, you can check it out. However, this is not. Why? Because phi of 1 is not 1, it's 0. Although the other properties holds. Now here comes an important principle known as the substitution principle. So what does this say? That if I have a um, two rings with an homomorphism pi, so I take this polynomial ring Rx. So it says that there exists a unique homomorphism from Rx to R dash such that when phi is restricted to R, what does this mean? Notice that R is sitting inside Rx. Why is that? Because if I take, let's say, A from R, that is also a polynomial, like constant polynomial, but it's a polynomial. So when it is restricted to R, I get pi, and the the polynomial x goes to A. Okay. So what would be this image? The image of f of x, it would be like this: pi goes inside this summation, and phi of ai. Phi of ai will be nothing but the smaller phi of ai times a to the power I, because phi of x is a. So this is the homomorphism, and this is unique. Now it can be also written with this diagram, which says that if I have R here, now this means there is exists a injective map, which is nothing but the inclusion map. That is, R is inside Rx. So if R is sitting inside Rx and there is a homomorphism from R to R dash, which is phi, then the principle says that there exists a unique homomorphism. Now we move back to polynomial rings again. Now we try to generalize this, but in a different fashion. So as you can see, we had only x here. So we replace this x and we put multiple variables, x1, x2, xn, many variables. And we similarly define the addition and multiplication. And I have kept this empty because uh, this multiplication you can define in the similar way, but it becomes difficult to write in this fashion. So there are sophisticated ways to write this, but I don't know much about them. Okay, so addition can be written in a similar uh, way, and we denote this notation rx1 x2 xn. Okay. Now rx1 x2 xn is isomorphic to rx1 x2 xn. Now what is this? Now this says that uh, this thing is again a ring, right? Let's say this is r dash. Now r dash x2 is again a polynomial ring with coefficients in r dash, and similarly we can continue with this. Now this is written like this because you can consider the coefficient of x1 as an element of uh, element of a ring of these variables. So these two are isomorphic. And why is that? We'll start with rx comma y is isomorphic to rxy, and then we'll use induction to prove this. I'm not proving this here, I'm just giving a sketch of proof here. So we start with r, and we you can see that r is sitting inside rx. Now this rx is sitting inside rxy. Hence we can see there exists a pi here from r to rxy, and that is just the composition of these two. And these are the inclusion maps. Okay. Now r is also sitting inside rxy. Now we will use the substitution principle here. That is, we have r sitting inside rxy. R, there is a homomorphism from r to rxy, and hence there exists a unique homomorphism. Now, as you can see, while proving our substitution principle, what we did for only Rx. However, it can be generalized for any polynomial. Okay. Now, what I will do, I will take Rx. Now, Rx is sitting inside Rxy. Also, it is sitting inside this thing, Rxy. Hence, there again by using substitution principle, there exists another homomorphism. Now, there exists homomorphism from here to here, and from here to here. Like from you can go forward, you can go backward. Now you can notice that these things have a special property, which makes it isomorphic. Now I will leave it as an exercise, but uh, now what property will make them isomorphic? You can try to determine that. Now here comes an important proposition. So let R be a ring. Now this proposition says that there exists exactly one homomorphism from Z to R, where R is any commutative ring. Now how do we define this homomorphism? We define it like this. We map n being an element of Z, to 1 plus 1 plus 1 n times. And for negative elements, we define it to be minus of 5. The minus of 5 of n means just the additive inverse of 5 of n. Now we can check that this is a homomorphism. We can also check that if there exists another homomorphism, that must be equal to this. Now, what are ideals? Now, ideal is a additive subgroup, and it's a non-empty subset of R, which has this following property. If I take any element in ideal, and if I multiply with another element in a ring, we get an element which is already in the ideal. Note that this need not be in the ideal. This another element which is multiplied, it can be in the whole ring. Now here are some examples. This is the curve phi or kernel of phi, that is where phi is an homomorphism. We can similarly define kernel as we did in loops. And this forms an ideal again. Now this is a new definition of ideal. So what I do, I take all the elements which I multiply with A, where R is in this is also known as the ideal generated by A. Ideal generated by A. Similarly, we can tell ideal generated by A1, A2, dot 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 A, and we define it to be this thing. Yeah, so that's it for ideals. Now we'll define quotient rings. Just like we had quotient groups, we will now define quotient rings. Now what is this? Now we have this notation here for quotient rings, and we define it to be the quotients of I, considering I as an additive subgroup. And we define the addition something like this, and the multiplication to be like this. Now you can see that why did we need to define ideals in this fashion, this odd fashion? Why do we need this? Because if we want this to happen, we want that if I multiply A with I, what does that mean? I is a set. So I multiply it with all the elements of I. Now I need those elements to be belonging to I. So I define the I in this fashion. And we got this multiplication as its consequence. So that is why we needed this definition. Otherwise, we could have just we should have just gone with the additive subgroup. Okay. Now here comes two powerful theorems, the isomorphism theorems, just like we had it in groups. So what I take two rings R and R dash with the kernel of f being k. So I have this R, I have this f, and R is sitting inside R bar. What is R bar? R bar is the R mod I, where I is an ideal. Now, if I is contained in K, where K is the kernel, then there exists a unique F bar from R bar to R dash. Sorry for this, there will be R bar here. Yeah, where this F bar goes from R bar to R dash. Now, if I is equal to K, and this F is surjective, then we can say that this F bar is an isomorphism. That is, R bar is isomorphic to R dash. Or we can say that R mod kernel of phi, kernel of F is isomorphic to R dash. Now we have the second isomorphism theorem, or the correspondence theorem, that says that if I take all the ideals containing K, where K is the kernel, then there is a bijective correspondence from this set to the ideals of R dash. Now, this means that if I get an ideal which contains k, then I'll get the ideal of R dash, corresponding ideal. Sorry. And how does this correspondence is defined? Is defined like this. If I take I go to phi of I here, I get I from here, and I go to phi inverse of I. Now, this phi inverse is not the phi inverse function. This just says all those elements where phi is applied and I get an element in I. This is the isomorphism theorems. I'm not proving it here, but you can take a look
Could you
at the
go over this
references.
once again?
Sorry?
Could you go over this once again, this slide?
Yeah, yeah. Okay, no problem.
Okay, thanks.
So what we had in the first isomorphism theorem, so we had this R, and from R we go to R dash. We go with the help of F, and we have this kernel K. What does kernel mean? Kernel means that all those elements which is mapped to 0. Now we have the canonical isomorphism from R to R bar, and this is pi. What does this mean? This means that I go from, let's say A is an element in R, and I go from A to A plus I. And this is the pi homomorphism, and it says, this theorem says that there exists a unique F bar. Now, how is this F bar defined? F bar is defined such that F bar of pi is same as F. Okay. Now, moreover, the first isomorphism theorem says that if F is surjective and I is equals to K, then this map is an isomorphism. That is, R bar is isomorphic to R dash. Okay. Now we have the second isomorphism theorem. That is, let's say we have a I here. This is I, which contain K. So if I know about this I will somehow know about an ideal of R dash. Now, how is this bijection defined? This is defined with the help of the homomorphism that is given to us. I take an element, I take an ideal I containing K, and I apply phi to it. That is, I apply phi to all the elements, and I get the new ideal, which is in R dash. Similarly, if I have this thing, I can go from here to here by applying phi inverse. Now, what is phi inverse? That is all those elements which are in which is mapped to I dash. This is shown by this phi inverse I. Okay, am I clear?
Yeah, perfect, thanks.
Okay. Now we'll move to principal ideal domain. Now, what is this? This says this all those integral domains whose ideals are of the form A. That is, all the ideals are generated by only one element. Now, here we take the example of Z. Now, what are the additive subgroups of Z? If I take 1 here, then I need to take 2, 3, minus 1, minus 2, minus 3, all of them. So, this is nothing but Z. Now, if I take 2 here, I need to take 2, 4, 6, minus 4, minus 2, minus 264, anything. So, these are the subgroups. So, N are the subgroups. Now, even if we take N comma M, that is the subgroup containing N and M, it will be same as the subgroup containing their GCD. So you can see that all the subgroups are generated something like this. Now, moreover, these forms a ideal. All these forms an ideal. Because if I take NR, let's say in this group, and if I multiply with S, I will again get NRS, which is already in this thing. So these are all ideals. And this can be a nice exercise. You can see that they are also equal as ideals. It just needs to use Bizarre's lemma. And similarly, you can check it out for Rx. All the ideals will have the form f of x. Now, once you do it for Rx, you can try it out for fx, where f is an field. Now, here comes a non-example, that is zx. Uh, Here, all the ideals are not of the form like this. And for example, take this example, 2 comma x. This cannot be represented as like this, f of x, where fx is a polynomial with integer coefficients. Okay. Now we were happy with integers. Then came rational numbers. Then came irrational numbers. Then we have real numbers. Now we are still not happy with real numbers. Why? Because negative numbers do not have square root. That is, x square plus 1 has no root in R. So need a we need a field or need a ring where this has a root. So we consider Rx mod x square plus 1. That is the quotient ring where x square plus 1 is the ideal generated by x square plus 1. We consider this. And what I do, I define I to be x plus x square plus 1. Okay. Now I square it, I square I and add 1. So I square plus 1 turns out to be x square plus 1 plus x square plus 1 in brackets. Now, why does this thing hold? Because we defined ideal multiplication and ideal addition. Now, this one is not the one in Rx, this is the one in Rx mod x square plus 1 or the 1 plus I. Let me write it here. This one means 1 plus I. Where I is this thing over here. X square plus 1. Okay. So I multiply I with I get x square plus 1, and I add 1 plus I to it, and I get this thing. Now what is this thing? X square plus 1 is already included in x square plus 1. So this is nothing but just x square plus 1, the ideal, 0 plus I. Now this is 0 plus I. Now this can be also written as just 0 bar. So we get a root of x square plus 1 in this thing. So what is so special about x square plus 1? Again, there is nothing special. We can again generalize it to be for f, where f is a monic polynomial. And this is nothing, and this is known as adjoining elements, because we are joining elements which need to satisfy this polynomial. Because we are not happy with just R, because R may not have all the roots. So we adjoin these elements, and that is how we got C. And we can get any root. Let's take a non-trivial example. For example, x squared. Now we need a non-zero root of x squared, let's say. So what do? I take this ideal, I add x to it, and I call it, say, epsilon. Now once I square it, I get 0. Again, you can see that x plus x squared is non-zero. So we get a non-zero root of x squared in this ring. And we define addition again, and define multiplication again, somehow like this. And this is known as dual numbers. You can play around with many polynomials and look for roots. This has nice application in physics, in mechanics. Now we come to product rings. Just like we had direct product of groups, we have product rings. That is, we just component wise add and component wise multiply. And we always have those other properties holding. That's it. Here are my references. I used Artin and Danguten Food, both nice books. That's it. Thank you.
Now we'll move on to questions. If anybody has any questions, they can ask now. Okay, since nobody has any questions, we conclude today's lecture on rings and modules. Thank you for coming.
Wait,
Okay,
Yeah.
will the slides be shared?
Yeah. Okay, I will share.
Where can I find the slides?
It will be posted in the website.